Hello everyone, welcome to this video. In this video, we are going to learn about the Temporal Convolutional Network, or TCN, using OpenMathAI. So, let's get started. What is a temporal convolutional network? A temporal convolutional network is a deep learning model used for sequential data and time series prediction. Unlike traditional regression models, which mainly predict the output from the current input values, a TCN uses a sequence of previous input values to understand how the system changes over time. A TCN works using one-dimensional causal convolutions and dilated convolutions. Causal convolution ensures that the model uses only current and previous values and does not use future information. Dilated convolution allows the model to look at both recent and older time steps without requiring a very large network. During prediction, the model receives a sequence of recent sensor values. The convolution filters move across this sequence and identify important temporal patterns. These learned patterns are passed through multiple dilated convolution blocks, and the final layer uses them to calculate the predicted output. We will use a multi-sensor temporal pattern dataset for the TCN model. This dataset contains 16,000 sequential data samples. The input features are Sensor 1, Sensor 2, Sensor 3, Sensor 4, Sensor 5, and Sensor 6, and the target output is target output. The time index column represents the order in which the measurements were recorded. The target depends on repeated temporal patterns and relationships between sensor values from previous time steps. During training, the TCN learns these short-range convolutional patterns and nonlinear relationships using a sequence length of 20. Once the model is trained, OpenMathAI uses a learned convolution filters and temporal relationships to predict the target output for new sequential sensor values without retraining the model. So, let's get started. Open OpenMathAI. In this demonstration, we use multi-sensor temporal pattern by using TCN model. Click Create New Project. Enter the project name as TCN. Choose a folder location to save the project, then click Save. To import your dataset, either click Load Example Dataset or browse for dataset to import your own CSV file. Once the dataset is loaded, verify that it contains all columns before proceeding to model training. Scroll down to view the first 10 rows of sample data. Click Continue to Configuration to proceed. Configure the dataset by specifying the input features and output target. There is also a feature called Ignore, which can be used for columns that should not participate in model training. Select the input and output columns manually or use Smart Suggest for automatic recommendations. There is one more feature, Signal Diagnostics. There is a free columns. First one is column its tell which features on the dataset like inputs and outputs name. Second one is VIF if it tells how much correlation of the features. Third column is status if it's OK, moderate, high, redundant, and constant. Review the selected configuration. Click Proceed to Model Design. Choose a model from the available machine learning models. OpenMathAI recommends suitable models and features based on the dataset. For this demonstration, select the TCN model. View the model overview, pros, cons, and real-world applications. Click Proceed to Training. You will see the selected model. Click Train Models. Review the training configuration. Test data split, which determines a percentage of data reserved for testing and validation. Review the model parameters and pre-processing settings. And also another feature is added that is trained from scratch or continue from use model. If you train this model before you use that option, modify the configuration if required. Click Start Training to begin the training process. After training is complete, review the following performance metrics. R-squared measures how well the model explains the variation in the output data. Range 0 to 1. MSE, mean squared error, measures the average squared difference between actual and predicted values. RMSE, root mean squared error, the square root of MSE. RMSE is expressed in the same units as the output variable, making it easier to interpret. Engine time, the time required for the generated model engine to execute and produce predictions. Lower engine time indicates faster model execution, which is important for embedded systems and real-time applications. Fit quality, an overall assessment of how well the model fits the dataset. It is generally derived from tricks such as R-squared, RMSE, and residual errors. Model accuracy is commonly estimated using the R-squared value. Example, R-squared equals 0.95 accuracy, almost equal to 95%. Click Fit to Window. You will see 3 types. Fit to Window, comfortable, compact. Then the Clear History. If you click that, it will clear the history before its trained model. Another is Deselect and select all trained model for export. Click View Curves. You will see the diagram of R-squared residuals and residuals diagram. Click Math and Code Preview to view the mathematical model generated by OpenMathAI. The TCN architecture, mathematical equations, generated source code. Open the Math view to visualize the complete TCN architecture. Maximize a window and scroll down to see the dilated causal stack, temporal blocks, training loss curve, and a complete network structure. The visualization shows how the TCN learns temporal pattern from sequential data. After training, OpenMathAI uses a learned network parameters to predict outputs for new input sequences without retraining the model. Return to the result page and click Deploy Status. Click Export Model. Choose the required export format: ANSI, FMU 2.0, FMU 3.0, Verilog RTL, VHDL RTL, Python Bundle, ONNX Hub. You can choose any of these formats and export. You can also download the free trial versions of OpenMathAI and Twin Simulate. Thank you. Stay tuned for more OpenMathAI demonstration.